Okay, good afternoon, everybody. So in this last class, we talked about Z transform, and we also talked about the inverse of Z transforms. So I'll just start the class now, then hopefully, so I'm starting the class now. Hopefully, I'm hoping that people are going to join in. So since, let me just see if I can mute. So I can see some people are already around. So, okay, you're already muted. So like I said, good afternoon, everybody. Okay, so the people that have joined, thank you for joining. So like I said, as I was saying, our last class, we talked about Z transforms. So in this class, we are going to be talking about the inverse. We'll talk about the Z transfer functions. And so before we start the class, I just want to say that if you have any questions, you can just post it in the chat. So I'll just move along. So I'm hoping that other people, they join also. So I'll just start. So the instruction is that if you have any question, just post it in the chat. Just post it in the chat. Then from time to time, I will look at the chats. Then I'm going to answer it. So before I start, I want to just mute everybody. I just want to see how I can mute everybody so that there will not be distractions. Okay, every one of you already muted. Okay, so I'll just start. So let me share my screen now. Okay, so I'm sharing my screen now. So before I start, can you all hear me? So in the chat, just if you can hear me before I start. Can you all hear me? Okay, all right. So a lot of people say they can hear me. Okay, so I'll just start. The rest, when they join, they will just follow up along. So, so we are going to be talking about Z transfer functions today. So I told you that this course is a continuation of what we did in 412. So in 412, we're in continuous time domain, but here in this course, we're in the discrete time domain. And in the continuous time domain, we know that if you have a system given by this, where U of t is the input and y of t is the output, we know that and g of t is a transfer function. We know that the relationship between the input and the output is given by this. So you know that from your continuous time representation. But from also in the time domain, so this in the Laplace domain, if you have U of S as the input and you have and you have g of s as a transfer function and y of s as the output, the relationship is given by this. You already know that. And if you're in the time domain, u of t is given by the input, g of t is the transfer function. The relationship between the input and the output is given by this, where this symbol is the convolution. So it's given by the input convolved with the transfer function, where this convolution is represented by this convolution integral. So you should have done that in your 412 and in your 322. So for this class, we want to know the relationship between u of z and y of z, where u of z is in the z domain. Now we're in the z domain now. So we want to know the relationship between the input and the output now in the z domain. So in order to do that, we are going to consider u of t. So u of t is going to be sampled. You know, u of t is in the continuous time domain. So to convert it to a discrete signal, it's going to be sampled in k steps. And also the output y of t is also going to be sampled in n steps in order to convert it into a discrete signal. So that's the principle we are going to follow. So we are going to start with the convolution integral. So the convolution integral is given by this. So this is the relationship between the input y of t and between the output y of t and the input u of t. And since u of t, we want to convert it into discrete time, we sample it in k time steps. So t becomes kt, where t is the sample time. Then so this is the convolution integral. So in place of this u of t, we are going to convert this u of t in the z domain. So you already know from the last lecture that the definition of the z transform. So if you want to transform u of t is given by this function, this summation. So, and this z minus k, the inverse z transform of z minus k, of z raised to the power of minus k, is this impulse function. So I'll just go to the z transform table. So from the z transform table, so I'm sharing my screen now. So from the z transform table, this is the impulse function in the time domain. This is it in the Laplace domain, and this is it in the z domain. So the z transform of this impulse function is given by z minus k. So that's why I replace z minus k with this impulse function. So let's move back to, let's move back to the lecture. So I simply replace this z minus k here with this impulse function. Then after that, we already have u of z. So instead of this u of t that is here, we are going to replace it with what we get here. So we are basically using this function. So instead of u of tau, we are replacing it with this. So which gives us equation 4. And the next step is to interchange the integral and the summation. So for those of you that, sorry, please, let me just, there's no way I can mute you. Please keep quiet, everybody. Please keep quiet, everybody. So I just want to mute everybody. Okay. So I'm hoping that everybody is muted now. Okay, so let me continue. So let me be sure if I've, okay, so let me continue now. So I simply replace this, what we got here, with this. Then now interchanging the sum and the integral, then rearranging it. So we just interchange and rearrange. Then we get this. We get this. We get this equation. Then the integration. So we want to do this integration, but the integration of an impulse function is a unit step. So this delta, this impulse is going to cancel out. Then the tau at tau is equal to kt. So the tau will become kt. So we arrive at this equation 6. So now, before we sampled the input u of t in k time steps, now we're going to sample the output in n time steps. So instead of y of t, we are going to replace it with the sampled form. And since we are sampling in n time steps, so t is equal to nt. And so the difference between this equation and this equation is that we replace t with nt, replace t with nt. And now we perform the Z transform of Y of T, the sampled version of Y of T. So this is the definition of the sampled version of Y of T, So the reason, for U of T, we sampled in K steps, but for Y of T, we are sampling in N time steps because we don't want to confuse the inputs with the outputs. So that's why we are using a different, variable. Then this is the definition of the Z transform. So in place of this Y of NT, instead of writing Y of NT, we simply replace it with this. So when we do that, we arrive at this equation. So since then the next step is we are going to collect like terms. So T is common to both, and so it translates into this. Then if we say that let M equal to N minus K, this function over here becomes this. That's if we say that in place of N minus K, let it be M. So M is equal to N minus K. We arrive at this. So this N minus K becomes M. Then this N, if you make N the subject of formula, N becomes M plus K. So you have M plus K here. So this N here, N is equal to 0 and K is equal to 0. So if N is 0 and K is equal to 0, so M is going to be equal to 0. So in place of this N, we replace it with M. So that's what we simply did. Then now, the final step here is to separate the M from the K. And so Z minus M plus K is equal to Z minus M, which we have here, and Z minus K, which we have here. So we are simply separating the M from the K. So we put the U of K here. We put the U of K here. Then we put the GMT. We put it here. Then we separate the summation. The M summation, we put it here. Then the K summation, we put it here. Then if you observe these two summations, you're going to see that this summation is equal to the G of Z. That's the Z transform of G, while this is equal to the Z transform of U of T, of U of KT. So because this is our definition of Z transform for G, and this is our definition of Z transform for U. So that means that the Z transform of Y is equal to the Z transform of G multiplied by the Z transform of U. So the summary of everything we've just done, the summary of everything we just done is to prove the relationship between the inputs U and the output Y in the discrete time domain. That's the basic idea why we are doing this. Then for those of you that just joined, I stated that the relationship in the S domain, that's when you're in the continuous time domain, the relationship between the Y, the output, and U of S is given by Y of S is equal to U of S multiplied by G of S. And in the time domain, the relationship is given by this, where this symbol is a convolution, So the proving I just went through, all these equations I went through, is to prove the relationship in the Z domain. And in the Z domain, we found out that the relationship between the inputs and the outputs is given by this. So I'm hearing some noises. It's unfortunate I can't mute the I can't mute everybody. So I will just let me see the people that okay. So everybody is muted here. Okay, so let's continue. So so we have been able to prove the relationship between the inputs and the outputs and the transfer function. We have been able to prove it by this. Let me check the chat if there is any questions. There are no questions. So I'll just continue. So we'll start with the first example. So the first example, you have this transfer function. And this transfer function is in the Laplace domain. So it's in the S domain. And the question says that you should find the digitized Z transfer function. So basically, you should convert this transfer function, which is in the Laplace domain, in the S domain, into the Z domain. So the way we do it, there are different methods in which we used to do it. And we'll be, in this class, we're going to be considering the different methods. So the standard method you can use is to put the equation, okay, is to put the equation. Okay, somebody is asking a question. Ma, would we need to prove the relationship between Y of Z and U of Z and G of Z? Okay, it's just for you to follow along in the class. So it's, please everybody, please, I'm hearing some noise. Everybody should be muted.
He gave me 5,000 that day. So I bought 500.
Please, everybody should be muted. I'm trying to mute everybody. So mute all. Okay. So I've been able to mute everybody. Okay. I've been able to mute everybody. So the answer to your question is that the most important thing is for you to understand it. The most important thing is to follow along the steps I went through, and you understand it. So that's the most important thing. So if you don't understand anything in what I've said, just write it in the chat. So it's not if you're going to be, the most important thing is just to understand it. That's what I'm after. Okay. But the examples, so there are 3 examples that I'm going to be doing for this lecture. So the examples are very, very important. The examples are very, very important. Okay, so let's start with the first example. So the question is, you are given the transfer function in the Laplace domain, and you are asked to digitize it. That's to convert it into the Z transfer function. And the first step you're going to do is that you're going to separate this transfer function into its partial functions. So I didn't go through the steps of separating it out. But when you break down this transfer function into partial fractions, you're going to get this. Then when you convert into the time domain, so the inverse Laplace of 1 over s is 1, and the inverse Laplace of this is minus 80. So then after converting it into the time domain, the next step is to use tables, the Z transform tables, to convert from the time domain into the Z domain. So the Z transform of 1 is this. So in the last class, we actually proved this. Then the Z transform of E minus T, raised to power minus T, is given by this. Then you have your minus A. So let me go to the Z transform table so that you can understand. So this is the Z transform table. So the Z transform of unit step, which is 1, is given by Z divided by Z minus 1, while the Z transform of exponential minus 80 is given by Z divided by Z minus exponential minus 80. So it's from the tables I got it from. So you should be able to know the Z transforms of all these basic signals. So it's important for you to know that. So let me go back to the slide, the lecture notes. Okay, so we arrived at this. The Z transform of this is given by this, and we got it from the tables. So you should know the tables, is very important. So when you do some manipulations and arithmetic to further simplify it, you're going to arrive at this, and T is the sampling time, is the sampling interval. Then after you finally simplify it from this form, you're going to see that the Z transform of the question, so this was what we started with. This was what we started it with, and this is in continuous time in the S domain. And you're asked to convert the transfer function to the Z domain. So we got the transfer function as this in the Z domain. So if there are any questions, let me check the charts. If there are any questions based on this example, okay. So I can't see any questions. So I'll just continue. I'll move on. Okay, I think we have a question here. Are we going to be giving the tables in tests and exams? No. The answer is a big no. So you're not going to be giving the tables. So you have to memorize the tables. So you're not going to be giving the tables. So you have to know that the inverse Z transform of 1, the Z transform of 1 is given by this, and the Z transform of this is given by this. I think there's some question. Why is still, you're not going to be giving the tables, sorry. So you have to know the, you have to memorize the tables. Then, so let's move on if there are no further questions. So we'll move on to discrete approximations. So in discrete approximations, what you are trying to do is to approximate the your transfer function from the S domain into the Z domain. The method we used just now is just the general method. And there are some cases where you might not be able to use this method we've used. And I'll be explaining further about why you cannot use this first method. when I finish this topic, discrete approximations. I'll be telling you when to use discrete approximations or when to use the method we've just used in the previous example. So I'll be telling you later. So you can also use discrete approximations. Okay, can you do a correction for the last assignment? Okay. Oh, okay. I'll take a look after the class. I would come back to your question after the class. Okay. So for this discrete approximation, the way we convert from the S domain, which is the continuous domain, into the Z domain, which is the discrete time domain, is to use this, is to say that Z is equal to exponential minus ST. And this representation, it gives us the exact Z transform. And the reason why, where I got this Z, in order to convert from either the Z to the S domain or vice versa, is that from the tables, I'll go back to the tables very soon. But from the tables, if you have an impulse function, the Laplace transform of the impulse function is given by this, and the Z transform of the impulse function is given by this. Then if you say that Z is equal to E raised to power ST, then if you say let's say instead of Z, let's say Z raised to power minus K, you would confirm that Z minus exponential and Z raised to power minus K is equal to this. So let me go back to the Z tables. So you can see that I'm referring to the Z tables a lot in this class. So the Z tables is very, very important. So this is what I took this from the Z tables, this line where my cursor is. This is the time domain, the impulse function, the Laplace transform of the impulse function. The Laplace transform is given by this, and the Z transform of an impulse function is given by this. So let's go back to the lecture. So that's where I got this line from. I got it from the Z tables. Then if using this relationship between the S plane and the Z plane, if you make Z the subject of formula, you will see that Z is equal to exponential raised power of ST. So the exact approximation to convert from the S domain into the Z domain is just to use this. So if you make S the subject of formula, I won't go through the maths. You would observe that S is equal to this. So just make S the subject of formula. And using this relationship is kind of messy because, okay, let's say that this is our exact approximation. And if we say that let X be equal to this, ln of Z, if we were to use this method, this particular method, S is equal to 1 over T multiplied by ln of Z. If we were to use this method to solve this example, so instead of S, we are going to replace it with ln of Z divided by T. We replace this S with ln of Z divided by T. The calculation is actually going to be very, very messy, and it's going to be very awkward, and leads to complicated terms, which is very, very difficult to manipulate, because this first method we use is actually much more easy. So this method of just equating Z to be equal to exponential ST it gives us the exact Z transform. But unfortunately, if we are to use this to solve any conversion we want to do, it's very awkward, and after the class you can try it on your own. It's very, very complicated, but there are other approximate methods we can use. Though using this, it gives us the exact Z transform, but it's very, very difficult and very, very quite complicated. So we have to look for approximate transformations that we can use to convert from the S domain into the Z domain. So the different methods you can use, the numerical integration and the pole-zero mapping. So the numerical integration involves there are three methods in the numerical integration: the forward rectangular rule, the backward rectangular rule, and the trapezium rule or bilinear transformation rule. So we'll start from the numerical integration. So for the numerical integration, let's say we start from the transfer function. So I just want to prove. So like I did when I started the class, I proved the transfer function in the Z domain. So I want to prove each of the numerical integration methods. So let's start with this transfer function. If you have this transfer function, then cross multiplying, you're going to get this. Then multiplying this, expanding out this left side, you're going to get uh, this highlighted equation. Then if we inverse Laplace this, the inverse Laplace of SYS is y dot. So is the y dt. The inverse Laplace of this is this. The inverse Laplace of this is this. Then now we just make this y dot the subject of formula and we get this. Then if we integrate both sides, you know, the integration of a differential function will give us the original function. So if we integrate this, we are going to get y of t, and you have to integrate both sides. You have to integrate both sides. So for digital representation, you know, we are still in the time domain. So for digital representation, we need to solve it at sampling instance from kt to k minus 1t. And we want to do the integration because we're actually converting this into the discrete time domain. And so we are going to integrate in order to sample this between this time step, from this time step to this time step. We have to integrate this particular function over this particular period, over this particular time. So from k minus 1t to k over t. So the difference between this equation and this equation is that I'm just putting the integration limit. Then the integration of y dot is y of t. Then if you put in the limits, you are going to get this. Putting in the limits. Then you are just integrating the right hand side. And so this equation here is just the same thing as this equation. So we said that y of t is equal to this. And we want to solve this. We want to solve this highlighted equation using, we are going to be using the three rules: the forward rectangular rule, the backward rectangular rule, and the trapezium rule. So here is the diagram for the three rules. So this is the forward rectangular rule. So I'll just explain the three. For the forward rectangular rule, you know, you are integrating between this and this in all the three cases. But for the forward rectangular rule, we said that the integration is given by the area under this curve. So you are starting from k minus 1t, but you are not going to end at kt. You are going to end, you are going to the ending point is also going to be k minus 1t. So you are maintaining the value of the function constant at the start of the integration. That's the forward rectangular rule. So if you look at the forward rectangular rule, you see that it underestimates the area under the curve, because where my cursor is not encapsulated in the area. So this underestimates it. So the backward rectangular rule says that the area from here, from this point to this point, is that you will consider the time limit at kt, then you keep it constant throughout the value of t. So if you observe from the graph, this particular integration method or approximation, it overestimates it, because where my cursor is not part of the area, and it's overestimating. Then the third rule is the trapezium rule. So the trapezium rule is that you will consider the start of the integration, that's k minus 1t, and you will consider the time at the end of the integration. Then you divide. You know that from here, 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 here is a trapezium. So that's where the trapezium rule comes from. So these are the three methods we are going to be using. So the forward rectangular rule, like I tried to explain, it says that the area under the curve is approximated by assuming that it remains constant at the value at the left hand, and the value at the left hand is k minus 1t. So you are just integrating, you are just saying that the area under the curve is given by the time at the start of the time, which is k minus 1t, and you keep it constant. That's what the forward rectangular rule states. So this was the equation we arrived at previously. So using the forward rectangular rule, says that this integration, in place of this integration, you are going to replace y of t and this u of t with k minus 1t. It's k minus 1t. So we are replacing, instead of this t, we are replacing it with k minus 1t. And instead of this t, we are replacing it with k minus 1t. Then you are multiplying by t. And the reason why you are multiplying by t is because the area, the area of a rectangle is length times breadth. So this, the breadth is given by t. So the distance from this point to this point is t. So that's why you have to multiply by t. So that's what the forward rectangular rule states. And when you, yeah, I just brought down this. So I brought down this here, and it becomes this. So Zoom is telling me that I have less than 1 minute more because I'm using the basic version. So I'll be stopping here for now. Then I'll be stopping here for now. Then you're going to join me using the next link.